Hello everyone. We're going to be looking at a leader election algorithm, a distributed computing algorithm, in the Hypercube. Alright, this is a distributed computing algorithm, so basically you have computers connected in a network. Let's say I have a set of computers like this, and they have connections between each of them. And the leader election problem is essentially trying to elect one person out of all these nodes to become the winner, the leader of the group. But the trick here is that all these nodes have to start at the same time, and they have to be running the same program. Okay, if you already knew which one to start the program from, then you already have a leader. Now, this is an interesting problem in distributed computing, and it's very well studied in the literature. So, why is this important? You run into scenarios where, for example, you wanna store a leader that initiates other algorithms, like finding a spanning tree, or algorithms that broadcast information, or just a main server node that sort of controls the rest of the network. So, let's say we've run the leader election algorithm, and this turns into the leader. Then you can start all kinds of algorithm from this single initiator without having to worry about conflicts from other ones. In fact, a spanning tree algorithm that has multiple initiators will fail, and it's quite difficult to have one compared to a spanning tree construction from a single initiator. All right, so finding a leader is very important. In some cases, you would have nodes that fail. So if a node fails, then the leader would handle this and basically notify the other nodes that, hey, by the way, this is gone. Now I'm going to have to figure out another replacement for it, and just to let everyone know. But basically, the leader handles the communication, handles the sort of the commands to the rest of the network. All right. There are all kinds of applications to finding a leader election. But again, the problem here is that we have before we found what the leader is, we have all the nodes starting at the same time, all the nodes in the same state, and in the general case, in the general graph, we have a running time of about O of E. E is the number of edges, plus n log n, where n is the number of nodes. Alright, so this is the general case, and we're quite content with this. But there's a powerful sort of component that plays into the complexity, the message complexity, which is prior knowledge. So if the nodes know about the topology of the graph, then you'll be able to optimize on this further. So for example, if you have a ring formation, then you'll be able to optimize on that. If you have a complete graph, let me complete this graph, then you'd be able to get algorithms that would do it in O of n instead of E, which is n squared, or n log n, which is worse than n. So knowing the topology of the graph is going to help you develop a better leader election algorithm. Alright, and today we are going to be looking at a leader election in a special graph called the Hypercube. Alright, in this paper, this is called the Optimal Elections in Labeled Hypercubes. Alright, it's a 1996 paper, but it's very well cited. It's cited over 50 times, so it tells you it's a decent paper in the literature, and it's got a lot of useful ideas in it. So let's take a look at what the Hypercube topology looks like. So Hypercube is essentially this. You start from one node, and then you go in one dimension. Alright, so this link becomes 1, this link becomes 1. Alright. I'm not gonna label them right now, I'm just worried about dimensions. Let me add another dimension. Alright. Let me duplicate them and add another dimension. So this becomes 1, 1, and this new dimension is 2. So I'm just labeling my links now. Alright. Let me add a third dimension. So it just becomes like this. And you can see why they name it Hypercube. Alright, so I just duplicated this entire square, and I'll just simply add that new dimension. Notice how we're just duplicating every single dimension that we add. We're just duplicating things. So this becomes 3 and 3. Sorry, this is 1 and 1. This becomes 3 and 3. This 3 here and 3 here. And yeah. We have 3 here, 3 here. Okay. And you can imagine this just duplicating further. Just duplicate this entire cube, and you have connections to from each one of these nodes to its image. Alright. And this graph topology is very useful, it's very popular because it has a diameter, which is the longest node path distance from one node to the other, longest possible of about log n, which is a dimension. Alright, the dimension of the hypercube. Alright, so this was a quick recap of how that. Okay, so I'm going to bring up an example from the paper itself, and we're going to try to do it ourselves. So here, might be too small, but you can probably see it. Alright, so we have here's a hypercube labeled with dimensions. So it's the same thing as the cube that we have here, it's just flattened out. Because remember, this is not a volume. These are just connections that we visualize easier in the shape of a volume because it makes duplicating them easy and so on. But it's the same thing as this. If you really look at it, try it out on paper, you'll find that it's the same thing. And here are the labelings for it. Alright. Now let's try out a sequence. Let's try out a sequence and create our own cycle in this, so we can arrive at something like this. So let's test it out. So the sequence here we have is 1 for 3-dimensional is 1 2 1 3 1 2 1 3. So 1 2 1 3 1 2 1 3. All right, so let's try it out. So I'm gonna go here. I'm gonna pick any random one. It doesn't matter where you start. You're gonna end up with a correct Hamiltonian cycle. So let's say I'm gonna go with this one. So I'm gonna go 1 2 1 3 1 2 1 3. Hey, it's just a ring. All right, and let me try this one example. So I'm gonna go different color. So let's go with this one here. Start with this one. So I'm gonna go 1 and then 2 1 3 1 2 1 3. It's kind of cool. It's a different looking thing, but it's still the same. It's still the same Hamiltonian cycle. Like it's not in the same order as this, but the nodes can't tell the difference. I can rearrange these nodes so that it'll still look like a ring. So just to understand that this sequence, this gray sequence here, it will work for any node no matter where you start. Okay, so it's almost like implicit knowledge by now. You don't even have to order them before you even start the algorithm. Alright. Here's the fourth dimension if it wasn't clear before. Okay, so let's begin with this distance-based one. So we have a sensor direction that's based on distance from the distance of nodes from each other. So in this example here, you can see the distance from this node 4 to node 0 is 1. Let's assume that they constructed a cycle, the Hamiltonian cycle that goes in this direction. Okay, so it's easy to see that this is distance 1. This is distance 7, right? It has to go all the way around here in the cycle to get to here. All right. here is distance 5. So how does this get to 5? Because you have to go through all of these to get to here, because that's what we saved as the Hamiltonian cycle. Okay, you can't just cut across. That's what we did here. We said, oh, it's the second dimension, I know where to go here. But I'm just labeling it with the distance on the Hamiltonian cycle that we saved. Alright? Okay. So in this case, in the case of a distance, we can actually take down the complexity all the way down to O of 1. And it's all based on this really sharp insight that the number of nodes, so the number of, let's say, not number of nodes, number of links with labels n over 2 minus 1 is exactly 4. If you use, let me put this as a condition, if we use gray code, the gray sequence, alright? There are other ways to construct a Hamiltonian cycle, but if you use the one we used before, the gray one, we're always going to end up with exactly 4 nodes, 4 labels, sorry, four labels of links that are exactly n by 2 minus 1. Now this might look weird, like, how is it exactly 4? No matter how big your dimension is, no matter how many nodes you have in the graph, you can have 1,000,000 nodes, you can have 8 nodes, you're still going to have n over 2 minus 1. That label is only going to be on 4, it's going to be used 4 times, and that's a really, really powerful insight, because that brings it down to a constant. All right, so let's see what that looks like. Essentially, it's really easy. It's really easy to understand. So I'm gonna draw Hypercube real quick here. I'm gonna try to do a 4-dimensional one. All right. Okay, fair enough. Let me draw another one. Okay, here's first square, second square. Alright, let me connect them and be patient with me while I connect them. I'm going to do it with the pencil just so that we don't end up with really thick lines, but there's nothing special about these. There's absolutely nothing special about these links. They're exactly like the other ones, just visually more pleasing. And I hope they can be viewed correctly on the video. Okay, so these links would obviously be labeled 4, and so on, right? So you have so let me say here, I'm going to say that links in this direction are 1, links in this direction are 2, this or this. Like, so horizontal links, vertical links are 2, depth links are 3, and then these hyperlinks are 4. Okay? Just to get a sense of what the dimensions are like. Alright, so when we have that, what this thing here says is, no matter how big your graph is, because you're trying to construct a cycle, there's going to be a point where you only pass it twice. So if you just think about it here, the way the gray code works is that it duplicates what you did in one dimension, and just takes it to the other dimension and connects it with a link. It's exactly what happened here when we did the 2D version. So with the 2D version, let's actually go through a full example, going from 2-dimension 3 to 4. Let's just do it. Okay, let's construct one. So I'm going to start from here. All right, so I'm going to go here. I'm going to go 1. So that's my first dimension. Let me put it down here. Let me put the gray code. Alright, so we have 1, 2, 1D, 3D, 4D, 5D. This video might be long, but it's good to actually go through the steps and see the details. So 1, 2, 3, 4, 5. Might not need 5, but so for 1D we have 1, 1. For 2D, we're going to replicate this with the rest. So 1 2 1 2. We have 1 2 1 3 1 2 1 3, and then repeat this twice. So we have 1 2 1 3 1 2 1 4. See, I just replaced the other one, and again the same thing again. So 1 2 1 3 1 2 1 4. All right, we don't have to worry about this yet. And you're gonna see this. This is such a simple but powerful idea. But okay, so let me go here. So first dimension we have 1 1. I'm not gonna go back. I'm just gonna go. Second dimension goes 1 2 1, and I'm not gonna close it. Right? I just don't want to close it yet. I have 4 dimensions to deal with. So 1 2 1 3, and then once I've gotten 3, I'm gonna repeat the exact same thing I did here. The exact same thing, but in reverse. And that's why they call the gray sequence the gray sequence in reverse, because essentially it's a reverse mirror image of what you just did in the lower dimension. So in 2 dimensions we went this direction, so when we cross to the 3rd dimension here, we're going to go just exactly the opposite of where we came from. So we're going to go back all the way up here and go back. So we followed 1 2 3, sorry, 1 2 1, so 1 2 1 3, and then 1 2 1 3 would close it back, right? But we're not done yet. We have a 4th dimension, so we're going to jump to the 4th one, right? So we're going to take this here. Now we repeat the exact same thing we did here. It's going to look exactly like a mirror image of what we did here. So we go 1 2 1 3 1 2 1. Okay, and the last thing we have to do now. Oh, I forgot an edge here. Sorry. So this has to go to its own image. All right. So the last thing here is for us to go 4, cross the 4th boundary again, and come back, and we have a full cycle that actually goes through every single node. Okay, let's just quickly go through it. 1 2 3. Bam! We're back to where we started. Alright? And that's good. And you'll notice that they look exactly the same. Right? The way I traversed this is I went this way, this way, this way, this way, this way, this way. Here I did the opposite. Where I started here and ended here, I'm going to start here and end here. You see how reversed it is? It's reversed in the order that you're going through it. But notice that even in the 2D case, there was this point here that we crossed. And we crossed it only once. Okay? As you go to higher dimensions, you see this point here? You cross it only twice. Why? Because if you think about it, you're trying to construct a circle. Right? This Hamiltonian cycle is just a cycle. It's a circle. So if you're going from one structure, no matter how complicated it is, to another structure, no matter how complicated it is, using the gray code, you are going through that one intersection between them only twice, just going in once and coming out. Okay. If you want to go to the 5th dimension, just duplicate this entire thing. So just duplicate every single one of these. Imagine taking an image, just flip it over. Okay, and connect every single one of these nodes to its own image, and label it as 5, as dimension 5, and create its own, and complete the gray code for it. Okay, instead of crossing to the 4th, remember how we remove every last link? Instead of connecting back, because we still have another one, we're just going to continue. So instead of doing this, we're going to go something like this. From here. So it's going to go something like this. Do the same thing here. Do the same thing that we did here, something like that. And come back here. Yeah, okay, it should have been like this. And once it's done here, it's going to go back to the left. So without this, ignore that this even exists now anymore. So in the 5th dimension, we're going to have crossings here only twice. Here's one, here's the second one. You can see the idea that if you take this now and replicate it to the sixth dimension, take this entire thing, duplicate it, and then connect every node to every corresponding node, you're still going to cross that boundary only twice. Once to go to that image and once to come back from that image. Alright, so we're done explaining this concept. It's very simple. I know it took forever to explain it, but it's a beautiful visual insight into how the gray code works. So based on this, and there's a proof by induction in the paper if you want to look at a more rigorous way of looking at this. Now, if we consider that this is true, okay, and we just saw that it is, then what we can do is we can simply say, let all the nodes start. So here's how the algorithm works. We just actually went through it. So once we created the Hamiltonian cycle, okay, every single node will check, do I have this label? Okay, there's only going to be 4 nodes that have this label. In the case of the 4-dimensional hypercube, the 4 nodes are going to be the ones with this label here. So we have 4 dimension, right? So for 4 dimension, what's this label going to be? So it's going to be 4 divided by 2 minus 1. So that's going to be 2 minus 1, which equals 1. Okay. Alright, so let's do a full example here in this case. So we're going to label an entire cube using the gray code. Okay. So alright. Yeah, I'm going to draw it like this. It might be better actually. So this is just another way of drawing the hypercube. So here, 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 bam, 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 bam. It's like another perspective view of the cube, and have the same thing over here. So okay, and we're not done yet. So we're going to actually do a full one this time. So let's do like this, and this one like that, and go down here, and go down like that. Okay. We're going to have to label this. Alright. So let's draw our Hamiltonian cycle first, just so we can get a sense of things, and then we can label the distances based on that. All right. So I'm going to start with this node. I like it. So again, just to be clear, here's where I consider it to be 1. Here's where I consider it to be 2, dimension 2. Depth would be dimension 3, and the 4th dimension is 4. Okay, that comes out of the page or something, or the cube traveling in time. All right. So going from here, I'm gonna go 1. Let me go up. Okay, 1. Go here. 1, 2, 1. And then instead of 2, I'm gonna go 3. And then the reverse. Just the mirror image of that. And then cross the 4th dimension. Okay. And then have the mirror image of that. So that whole 3rd dimension thing, just have a mirror image of it. Okay. So we're going to go here. And then just to close it, we're going to jump back through here. Okay. Yeah, that looks correct. Yeah, we only crossed it twice. That sounds good. Alright. So now let's start labeling. I'm going to use a pen for this. I hope you can see this. Um, maybe a black one? No, a blue one. Okay, so the distance from here to here on the Hamiltonian cycle is 1. Right, so this is 1. Is this visible? Yeah, certainly. Okay, so this one here is 1. From here to here, that's 1, 2, 3. So that's 3. From here to here, that's 1, 2, 3, 4. It's 1, 2, 3, 4, 5, 6, 7. Oh, yeah, it's gonna go all the way around, right? Let's try it again. So, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Oh, sorry. 1, 2, 3, 4, 5, 6, 7. 7. So this one here is 7. One note done. 16 to go or something like that. Okay, so only 8 to go. No, 16. So we have distance from here to here. That will be just running through around the entire cycle. So that would be 15. Let me just quickly check. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Oh. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Sorry, 15. Why is 16? Yeah, distance from this to this is 15. Okay. This is going to take a while, so I'm probably going to pause the video halfway through. But you get the idea of how we're constructing it. Alright? So 1, 2, 3, 4, 15, and here is 1. So coming down here, this is 1 and 15 and 1 and 15. You notice the pairs, right? The 1 and the 15s. These are easy to do. I'm just going to go around the cycle and do them quickly because they're fairly obvious. So 1, 15, and yeah, because actually let me clarify that it goes. I just need one arrow to show that it goes in this direction. 1, 15, 1, 15. Alright, I'm pausing the video for a sec. Alright, so I'm done labeling the graph here. Every single node has 4 labels, because we have a dimension 4 hypercube here. And you'll notice that on each link, one side is labeled, if one side is labeled with M, then you're going to have the other side labeled with 16 minus M, because the total number of, the length of the cycle is 16, so obviously if you go from one side to the other, you take M steps, then for the rest of the cycle is going to be 16 minus that. So that's why you find things like 1 and 15, 9 and 7, 13 and 13 and 3, so 13 here, going all the way to 3. Okay, so we're done labeling. So here's what we said from the previous the insight that we got from the paper. It said that the number of links that have n divided by 2 minus 1. So what is that label? That label here is 16 divided by 2 minus 1, which equals to 7. Right? So it said that we're going to find exactly 4 of these labels. Let's try to find them. Alright, so let me grab a different color. Let's try pencil. Okay, 7, 7, 7. So here's 1, 7. Okay. Brightness, too much brightness. Okay, here's 1, 7. Here's the other 7. Here's a third 7. And here's a fourth 7. Tiny little 7. Okay, can't see any other 7s. And just equally n divided by 2 plus 1, 16 divided by 2 plus 1, which equals 9, is also going to be 4. Why? Because there's exactly four labels that are 7, and we have 16 minus 7 is 9. So for every 7, there's going to be corresponding 9. So we're going to have, this is a label 9, this is a label 9, this is a label 9, and where's the 7th one? There we go. Label 9. Okay. So these 8 nodes, okay, these 8 nodes that are connecting all the links that are labeled 7 and 9, okay, all of these nodes, the total number of them is 8. I'm running out of space. The total number of these nodes is 8. Right? So I have about 8 nodes. And I just showed you a massive example. This is obviously just dimension 4, but you can take this to a million dimensions if you can imagine, and you still get only 8 nodes that have n divided by 2 minus 1 and n divided by 2 plus 1 labels on their links. So within these 8 nodes, we can elect a leader. Alright, so for every other node, so the key here is that to say that for every other node, check if I have these. So for all the nodes, first of all, check. Do I have an n divided by 2 minus 1 or an n divided by 2 plus 1 label anywhere on me? If I don't, then I'm not a leader. I'm already a follower. Okay? What's left is the 8 nodes that are going to compete for it. Right? So right now they're candidates. And they know themselves. I don't have to send out messages and try to figure out. They know themselves because they can just look at their link labels, their own link labels, because they're locally known. And they can just see if they have a 7 or a 9. Alright? And once they do, these 8 nodes are going to form a cycle. I'm going to try my best to draw it without ruining everything, but let's imagine here. Let's say, alright, I'm going to use green, maybe blue. Okay, blue. So here are the 8 nodes. There's this one here. There's this one here. There's this one here. There's this node. And the matching ones. Okay. And we can form a cycle easily because they all get connected to each other. So within that cycle, I can just try to elect a new candidate. And you can use any of the regular... so we have a cycle here that connects all of them. And you can use any of the regular... So it essentially becomes a ring. Just 8 of them connected in a ring. You can use... There are simple trivial O of n square ring algorithm, election in a ring. But the thing is, we have 8 nodes always. It has nothing to do with n. So even if it's O of, what is it, 8 to the power of 2, so 64, that's still O of 1. That's a constant. It doesn't change no matter what you do. Okay? So this is great. We're done. And that's the message complexity. It's an O of 1. Okay? But we still need to broadcast and announce which one of these 8 won. Which one actually became the leader. Okay? So that takes an O of n. So let me separate this. So that takes an O of n to broadcast. It's a simple broadcast. That leader now becomes the initiator, and we're sort of done. So we do a broadcast, and that would take O of n. It's just a regular broadcast with like flood or something like that. All right. Now, what's really unique about this algorithm and the next one, we saw the distance. We just did the case for the distance sense of direction. We're gonna do the dimensional, but what's nice to remember about both of these is what makes them unique is that they don't. The method in the paper doesn't build this spanning tree before it starts. So if you build a spanning tree, explicitly build a spanning tree before you start doing any of these stuff, it becomes trivially easy to do it, because you can just find the leaves and start sending messages. Treat the leaves as your initiator, because all the leaves have 1 degree, and just treat them as your initiators, and it sort of becomes like a saturation algorithm, which is linear, so you don't run into n log n and all that kind of stuff. But here you don't even need to do that. You just figure out, do I have an n divided by 2 minus 1 or n by 2 plus 1? If I do, let's compete for it. All 8 of us. Alright. So now we move on to, so that was the dimension one, and we're done with that. Now we move on to the, that was the distance-based one, and we'll move back into the dimension-based hypercube, and we'll look at the algorithm that can solve it. The paper essentially does it in O of n. And we're going to take a look at how they arrived at this. Alright, so we come to the scenario where we have the hypercube labeled based on dimensions. And every node looks like every other node in terms of the labels. Right? In the distance-based one, they weren't symmetrical. So the nodes could have different types of labels than other nodes, because it depends on their position in the cycle. But in dimension-based labeling, they're all the same. They're all going to have each dimension represented with 1 link. All right. So the one algorithm that this paper proposes for this is based on the concept of a tournament. So you're familiar with this already. You know how semifinals and quarterfinals competitions work, where you have 2 compete and 1 is the winner, 2 compete and 1 is the winner, and 2 compete here and 1 is the winner. And you can just mirror this. Again, we come to the whole mirror analogy like before. And this is really because of how mathematically, I missed one here. So these 2 compete. Let me draw it properly. Because of how recursive the way the hypercube is, we get to see these sort of repetitions. So you're familiar with this concept, right? Each of these 2, when one of these 2 wins, this becomes the representative. We have an A and B. So if A wins, then A becomes the representative of both of these. Right? If I have a C here, that one C is a representative of both of these. And let's say D, so B lost, D lost, C won. Now within A and C, let's say A won. So within this whole thing, A became the representative. Right? So A is a representative of this entire branch coming out of this line. Right? And the same thing here. So you have something here, this comes out, there's something here, this comes out, and all the way until you have 2 left, and one branch is stronger than the other, and you're left with the leader. Okay, this was just a quick look at the style of the algorithm itself, but let's look at it in more details properly. So let's take a look at a 3D example. So a 3-dimensional one. I'm going to have a node here, node here. I'm going to have it more spaced. And at the end of the video, we're going to do a full 4-dimensional example, but just to get the idea of how it works, let's do this. Yep, that's right. Okay. Yep, that's the hypercube in 3 dimensions. So let me give them values. This time I'm going to give them actual values. So remember we were saying we had unique IDs, so let's say 3, 16, 9, 7, 8, 4, 2, and 5. Okay. Now again, I could go along and label every single one of these, but it'll be easier just to do it here, just to keep a clean diagram. We're gonna have 1 is any that goes in that direction, 2 is all of the ones that go in that direction, and anything that the third dimension is going to be the one that crosses between the two of them. Okay? Alright. And just to be complete, I'll give you an example. Here's what it looks like when I label one of the nodes. So this becomes 1, 2, and 3. Okay, so this is the link labeling. This is the actual node ID. So this is the value that we're trying to compare. This is the value by which we're able to elect the leader with. That's how we're comparing stuff to each other. It's the value of the node itself. It has nothing to do with the labeling. Okay, the labeling is going to be the same for everything else. So here is going to be 2. It's going to be dimension 1, and this is dimension 3. And in this case, because we're doing dimensional, they're going to be symmetrical. So 2, 2, 3 will be here 3, and so on and so forth. All right. Okay, so here's how the algorithm works. Start with the first dimension. So for dimension 1, so for the first dimension, here's what I'll do. For each one of these, I'll compare them to each other. So for each node, I'm just going to look at the node along the first dimension and compare them. And whoever wins gets to hold that group. So let's just do it. So 16 and 9, 9 loses. Let's say we're trying to find the maximum. Our leader would be the one with the maximum value. So we have 16 and 9. 9 would lose, right? So 16 would be our victor, and I'll keep the green for the 4-dimensional example. It'll be more detailed. So we have. I'm gonna just highlight this in a circle like that for now. 7 and 3, I'm gonna cross this 3, so 3 lost. Let's highlight the circle. 8 and 2, 2 loses. 5 and 4, 4 loses. Alright. So this is the result of the first dimension, right? I've crossed out a lot of nodes, and they're now followers. They know themselves as followers. I'm left with candidates for leadership. Okay, and the reason why I drew these is now, if you look within that circle, the only number left is the one that represents that entire group. Okay, so here the only number left is 16, and here's 7, and here's 8. So once I've done the first dimension, if we move on to the second one, and notice that I went from in the first dimension, I ended up with 1, 2, 3, 4 nodes left. I crossed out 4 and 4 nodes left. Okay, so let's see what the second dimension has. So for this, when we do the same duel, the same attack fight sequence in the second dimension, let's just do it here between this giant group and this giant group here. So between these two, this is the number representing this blob, this is the number representing this blob, 7 and 16. 7 loses. Between this blob and this blob, here's the second dimension. This blob and this blob, we have 5 and 8, so the 5 lose. See, they're not. 5 and 8 are not even connected, but let's just go with it for now, because the 5 represented this blob, so 5 loses. Now the 8 is left. So we eliminated 2 more nodes, and we're left with 2 nodes left. All right, we're starting to see a pattern. Now, if I draw another sort of grouping, the only number still alive in this group is 16. The only number still alive in this group is 8. And now let's do the duel in the third dimension, which means I'm going to send messages along that dimension. When I say duel, I mean we're only sending messages to compare values along that dimension. So let's say that 16 represents that entire group, and 8. So 16 versus the 8, because we're crossing in the third dimension, the 8 loses, and the 16 becomes the leader of that entire group, which just happens to be our problem graph, the entire graph. Okay, so we're left with 1 node, which is the leader. Okay, so assuming that we can do this, assuming that we have ways to actually emulate this grouping and this representation of an entire group, this is essentially how the algorithm works. So an interesting thing is that at every dual stage, when we fight, we lose half the nodes. We turn half the nodes into followers, and the other half are still candidates for leadership. So it's good. It means that overall, how many steps do I have? I have log of n steps. Okay, and this is key. This means that it's very finite, and it's not linear, which is nice. We'll see how we can get an O of n result. Okay. So the key idea here is that if I go back to the example and erase all this, I don't want to draw the hypercube again, so let's just erase all this real quick. Alright, all clean again. So let's examine just the first step between two nodes. Let's look at the 16 and the 9. So the 16 will send an attack message to 9 saying surrender, and 9 will send a message to 16 saying surrender. And the 16 will receive 9's message and say, I'm bigger in value, so I'm obviously the leader of this duel. So I'm the winner of this duel. So I'm going to label the 16 as the duelist of level 1. Sorry, 1 plus 1. So in this case, level 1 is K. So let's say the level is denoted with K. Okay. I'm gonna label 16 as a duelist. It's still in the contest. It didn't lose. Okay. I'm gonna use green here because it's more clearer. Duelist of level K plus 1. So in this case, it was level 1. 1 plus 1, which is 2. Okay. A duelist of level 2. And 9 is a loser. When it receives 16's message, it will just already know that it lost. It doesn't need to inform 16 that it lost. It already knows that. So we call it a S for second. Came in second place, and level 1. Okay, just level K in this case. So let's go around and label all of these. So 3 and 7. 3 loses, so that's an S1, and here it's a D2, and here 8 and 2, this becomes an S1, this becomes a D2, and here 5 and 4, this becomes a D2, this becomes an S1. Okay, so the S sort of denotes the end of the line. At which level did you lose the duel along that dimension? Okay. So we take all of the nodes that are still labeled D2 and somehow get them to fight against each other along that dimension. So we're done with the first dimension. We label all our nodes. We know the losers. But what the losers will keep is the path that the winner took to get to it. So the path sequence here from 16 to 9 was just 1, right? This was the path that 16 took to get to 9. It just went 1, right, in dimension 1. So 9 is going to store that. So if anyone tries to attack this group through 9, 9 will just say, oh, you want 16, you don't want me, you want this node to fight you, because this node now represents this group. Let's try it out. So we said that 16 and 9, so I'm gonna highlight this this group. Okay. So the 16 is now representative of our group because it's the D2. And in this case here, again, the grouping is just a virtual thing that we use to help us understand, but there is no real grouping happening. It's implicit. and it helps you get a better visualization of what's going on. So we have a 3 and a 16. They fight along the second dimension. Remember, we're in the second dimension step, so nothing happens along any of the other dimensions. We're just dealing with the second dimension right now. So 3 and 16, the 3 loses, right? So it ends up, 3 is already a loser. So it doesn't even compare with 16. It doesn't even send a message, an attack. It doesn't send an attack at all. So here in this case, there was an attack that went in and an attack that went back. All right. In this case, there's an attack here, but when the 3 doesn't send an attack to 16 because it's already a loser. It's already an S1. It cannot fight in a level 2. Okay, only D2 can fight in a level 2. S1 cannot fight in a level 2. It doesn't have that level yet, and it won't because it's already lost. So when 3 receives this message, it just forwards it to 7. Okay, but in the first attack that 7 sent to 3, 3 received the sequence of nodes that 7 had to take to reach 3. So in this case it was 1. Right? So when 3 receives the 16 attack in level 2, it's going to say, oh, you want to go to 1 actually. You're going to have to take this detour. You want to go here. So 16 is going to say, okay, I'm going to 3 is going to forward 16's attack to 7. Okay. 7 is going to obviously fall, so it's going to go S2 to 16's attack. Right? Now 7 doesn't send the response back to 3 and 16 because that would be violating the second dimension. We don't want to go through this way. Okay, so first of all, 7 just realized that it lost, but it also, before it realized that, because this is an asynchronous environment, it sent an attack. Where did it send it? It sent it along the second dimension, because we're in the second dimension here. So 7 already sent this. Okay, 16 doesn't know what the answer is. It doesn't know whether 7 is it's actually 7 or 17. It has no idea yet because it hasn't received an attack yet. So let's do this then. So 7 sends an attack to 9, right? So 9 is already a loser. So 9 says, okay, here's who you want. You want 16, so just go 1. Okay, so it's gonna forward the attack to 16. 16 is gonna receive 7's message and say, okay, well, I'm obviously bigger, so I am D3. Okay, and we just close this up. Just in our mind, just close this group up. And obviously the winner here is 16 within this group. It's D3. No other node is D3. Okay, let's do this again here a little quicker, just to get the concept right. Okay, so in this group we have 5 and 4. In this group we have 2 and 8. Now they talk to each other. There was an attack here and an attack here, an attack here and an attack here. Now in the second dimension, 2 is not going to send an attack because it's a second. 5 is going to send an attack for sure because it's a duelist. And 2 is going to say, well, you want 8. So, and 8 had already sent its sequence to 2 as 1. So we're just going to forward it to 8, and 8's going to say, oh, I'm good here. So it's going to label itself as D3. Okay. 5 doesn't know yet whether it lost or won. 8 is going to send an attack. 8 doesn't reply along the way back. So 8 sends an attack along the second dimension, because we're still in the second stage, second dimension. 4 is a loser, so it just forwards it to 5. Forwards the attack to 5, and 5 receives the 8 message and realizes that it just lost. So it becomes S2. And we end up with another D3 in this group. So D3 here and a D3 here. So this is the second stage done, and for the third one we go, okay, each node that is still a dualist sends a message along the third dimension. So S1 loser, S2 loser, S1 loser, 16 is still alive, so 16 is going to send it along the third dimension along here. So here's an attack that's going to arrive here at 4, right? But 4 is an S1. Okay, so it knows that it's a loser, so it's going to have to forward the attack to someone, right? It's going to forward it to whoever beat it. It's not going to forward to 8. It doesn't know that how to get to 8, but it knows how to get to the one that beat it, which is 5, right? Because with every attack, I'm sending the sequence of traversal that I took to get to you. I send that with the attack, and the loser saves a copy of that with it. So we have 16 to 4. 4 is going to forward it to the one that beat it, which is 5. And you can look at this number here to figure out which one it beat it. 5, and 5 is a loser at level 2, so it's going to send it to it's just going to send it along the second dimension. It's not me, who you want to fight. And 2 is going to be again just forwarding the attack. Because it's an S1, it's going to forward the attack to whoever killed it, which wasn't 5 or 4, it was 8, so it's going to forward the attack to 8. And when 8 receives it, it's like, I'm D3 and you're D3, I get your message, but hold on, you're 16 and I'm 8, so I'm obviously out. So it becomes an S3. Okay, now 8, as the only other node that was also D3 when we started the stage, is going to send an attack along the third dimension. It's going to arrive at 3. 3 is going to forward it to whoever killed it, which was at stage 1. So look in the first dimension, because you already have the sequence here with the 7th first attack. I know it sounds a little confusing, but if you try it out, it's very simple to understand. So 3 is going to forward it to whoever killed it, which was 7. 7 is going to forward it to whoever killed it, which was second stage, which was 9. So it's 7 to 9, and then 9 is going to forward the message to whatever killed it, which was at stage 1. So it's going to forward to 16, and 16 is going to receive the message and realize it's the winner. So D4. So once you arrive at the D dimension, right? So once you arrive at D, so the node that has a dual of the dimension of the graph, that's your leader. You're done. There's only going to be 1 left, because remember we said we halve the number of nodes every step. Okay, so that's going to be the 1 left. All right. So we're going to do we're going to do a four-dimensional example, and I'm going to draw a hypercube in just a minute. And after that, we're going to take a look at the complexity and why it's O of n real quick. Okay, so I'm going to draw the hypercube and be right back. Alright, so here's the 4-dimensional hypercube, and we're going to start the algorithm. So, again, just a reminder, this is based on dimensional labeling. And remember when we said that node labels, the binary node labels that you normally associate with Hypercube don't matter? They don't. We just really care about the IDs. The unique IDs here are not the binary labels, they're just the values that you're trying to elect the leader based on. And what really matters is just the link labels really matter. So, just out of completeness, 1, 2, and depth is 3rd, and the 4th dimension is the one coming out. And I like to draw it this way because it minimizes the crosses between the links. Alright. So let's start the first step, and we're going to try to count the number of steps that we do so that we can show that it's O of n, but let's see the first dimension. So step 1. There should be in total 4 steps because we have 4 dimensions. So step 1, let's just do it. So 3 and 12, 3 dies, 12 wins. Let me use this. So 12 is the winner here, and 3 just becomes a null that just forwards stuff. Alright, so this becomes an S1, and it received from the attack. So it received an attack, and this sent an attack, and it received a 1, and so did 12. 12 received the 1 as well, which is the path each one of these took to reach the other. But we're just going to concern ourselves with what the loser stores, because the winner doesn't store any path to S1. It just stores it to every node. Just stores the path to whoever killed it. Okay, so I'm not going to try to repeat myself too much in this, and see how we can just go through it. So 12 and 3. 3 is S1. 12 is D2. 10 and 1. 10 becomes. You can assume that we have sent an attack, so 10 becomes D2. 1 becomes S1. Okay. Here, 7 loses, becomes S1. 4 loses, becomes S1. The 9 wins, becomes D2. It can move on to the second level, and so does the 15. Okay? So, attack, 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 attack. Okay? We're all in step 1. We do nothing in any other dimension. We're only sending attacks in one dimension. Okay, so here 2 loses, 5 loses, 13, 6. So all of these are labeled S1. I should have labeled them L for loser, but whatever. That's what the paper uses, so it calls them seconds. They came in second place. But I think they just call them losers. It just makes it sound better, I think. So D2. I'm just checking again that I don't have any duplicates here. No. Okay. D2, and this becomes D2. Okay, step 1 done. And we sent exactly 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Each node sent one node. So each node sent one message along this. So we had N messages. Okay, let's do step 2. We have in the second dimension we have these two don't send messages. We're left with only 8 nodes that send messages, the winners. So this guy sends an attack, this guy sends an attack. So they duel each other, 10 and 12. 10 loses, so the 10 eventually folds, and we have becomes an S2, and the 12 wins, becomes a D3. Okay, and remember the 10 stores the path that 12 took to get to it, so it's gonna store the 2, right? That's the dimension that it took. That's the label that it took. Over here, 9 sends an attack along 2. This doesn't send an attack. This sends an attack along 2. So 4 is gonna forward that attack to 15 because it knows which one killed it. So every loser knows the path of whoever killed it. I'm gonna say it over and over again because that's the fundamental point of the whole algorithm. That's how the whole algorithm. Whoever lost knows the path that the winner took to get to it. Okay, so 9 sends to 4. 4 forwards the attack to 15. 15 realizes it's bigger, so it announces itself as D3. 9 doesn't know yet, but 15 sends an attack to 7. 7 forwards the attack to 9. 9 realizes it's an S2. So 9 just lost. Okay, and the 15 is still a winner. Alright, same thing here. 2 doesn't send, 6 doesn't send, 11 sends an attack, 16 sends an attack. So the 11 loses, becomes an S2, and stores the path that 16 took to it, which is just 2. In this case, 16 becomes a D3. Alright, here these two don't send attacks, but this one does, and this one does, and they compare against each other. 14 loses, becomes an S2. 15 wins, becomes a D3. Alright, and we're done stage 2. How many messages do we send? Okay, so we started with, it's going to be some multiple of n by 2, right? Because we just halved the number of nodes that were active. We just halved them. Each one of these sent a message, so n divided by 2. But then sometimes these messages got these attacks got forwarded, right? So if there was anything forwarded, it would have been forwarded by at most in step 2 it would have been forwarded by at most once. So it becomes an n divided by 2, okay, and at most they're gonna forward it to one step below them, right? You can't go any further than that. So it's n divided by 2 messages initially, and then plus at most the diameter between step 2 and step 1, which is just again n divided by 2 in this case. So that's the worst case, right? I'm just describing here. I'm describing the worst case. I didn't actually count them, but that's the most number of times that it'll get forwarded. And it'll get forwarded with a single message. It won't be forwarded like a bouncing. Nothing like that yet. Okay. So let's do step 3. Alright, so we're gonna go in the zooming direction. So these don't attack. 10 doesn't attack, it's dead. 12 attacks, so 12 sends an attack in the 3rd dimension. 4 admits defeat at 1, so it forwards the attack to 15. Right, just forwards that attack to 15. And 15 realizes, oh, I'm a winner, so D4. 12 doesn't know yet because 15 sends an attack here. None of these here attack, so we don't even count those. 15 sends an attack along the 3rd dimension. So 3 is the loser, realizes I need to forward it to whoever killed me, which was 12, so forwards it to here. So 12 realizes I just lost because it got 15's message, and it becomes an S3. Alright. Let's do the same thing here. These don't send. Now let's look at this one, doesn't send either. Let's look at the only ones left. Oh, I do have a duplicate. 15 and 15. What do I have left? 1, 2, 3, 4, 5, 6, 7, 8. I'm missing an 8. Ay. Okay, so I'll just here's what I'll do. I'll just switch these two together. So I'll make this I'll still make it work. So I'll make this 15. I can erase it. Yay. So we want to make this work. So I'm missing 8. So I'll call this 8. And I'll call this 12. Yeah, I didn't need to erase it. So it still works out. 8 is better than 7, and it's better than 4. And it lost to 9. It should have lost to 9. So 9 would be the D. 9 would actually be D3. So 9 would be D3. This guy would be S2. Okay. And 12 would not have lost just yet. In fact, it would send them attack message to 4. 4 would forward it to 8. 8 would forward it to 7. 7 would forward it to 9. And 9 would realize it just lost. So 9 becomes an S3. Now, 9 sent an attack along the 3rd dimension, right? Over here. So 9 to 10, 10 lost, so forwards it to whoever killed it, which was 12. And 12 realizes, oh, I just won this group. Alright, so it becomes a D4. Sorry about that, a little mix up, but now we're back on track. Alright. So, 15. So I should probably just take this out. This does not exist. Okay. And let's draw it to be complete. That was that entire cycle. this was not there. There was this and that. Okay, good. So we can count them at the end and see how they are actually O of n. Let's see. So 14 and 15 sends a message to 14. Nope, that's D2, step 3. So we're gonna go in this direction. Wrong color. In this direction and in this direction. These are the only two that are still active. They're still D3. So 15 sends to 6. 6 forwards it to whoever killed it, which was 16. So forwards the attack here. 16 realizes it's just 1, so it becomes D4. 15 just doesn't know it yet. 16 sends a message to 13. 13 forwards it to whoever killed it, which was 15. So send them attack here. And 15 realizes it just lost, so it becomes an S3. Alright. So we can see a lot of nodes are already gone. We're actually just left down to 2. So now we go to the step 4. Okay. So in step 4 we only send messages in the 4th dimension. So there's a message here, and the 8 sends a message along this direction. See the line here. Okay. So 16 gets the message to 3. 3 sends the message to whoever killed it, which was 12. 12 sends the attack message to whoever killed it, which was no one. Sorry, not 8. Oh, I forgot to put this as black. 12 is the one that's still active, so let's take this out. Ah, this is getting messy, but it's okay. I think you get it. So 12 sends that in the 4th dimension. Okay. So it sends it to 12. 12 realizes, oh, I just got a message from an attack message from 16. I just lost. Okay. So it becomes an S4. 16 doesn't know it yet, but 12 sends a message to 6. 6 sends a message to whoever killed it, which was 16. So there's an attack, and here's another attack on 16. 16 realizes it's just 1, so it becomes D5. Okay, so that's D of K plus 1, right? So 5 is equal to D of dimension plus 1, which means we just found the leader. Okay, and it's 16. Looks correct. Okay, let's do a quick count of the number of edges that we sent. We have, I'm going to go from left to right. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 41. Okay. 41, 42 are roughly that number. So in total we had about, in this scenario we had about 40, approximately 40, which sounds right. We're still not sure whether it's n log n or it's n. So is it a constant times 16, or is it 16 times log 16? So it's almost 16 times 4. Which one is it? Is it this one or is it that one? So we're going to do just a little bit of analysis to close this section, and we're going to be done with this video. So we're going to take this notion here and formalize it a little bit. So at every stage, at every step, okay, we know that there's going to be, let's say step I. So at step I, okay, we have n divided by 2 to the power of I minus 1 nodes that are active. Okay, these are dualists. Okay, dualist attacks. So each one of these is going to send one attack, right? Okay. So they're going to send one attack each. Now, how many times does it get forwarded? Well, let's see. In step 1, you're gonna at most have it being forwarded the diameter between the steps. Okay, so from step 1 to step 0, the diameter is 1. So at most you're gonna have +1. Okay, but that 1 is each one of these attacks might actually go through that. So I'm gonna put these in a bracket here. Okay, so you have at step 2, again, the diameter from step 1 to step 2 is about 1 diameter, is the maximum length that the attack can be forwarded, is also 1. So at step 2 it'll be n divided by I to the power of -1 into 1 plus 1. So this 1 here stays constant, but this one changes, right? Because I could go in step 2, I can go either 1 along my dimension or 1 plus 1 along the second dimension. So I can forward it twice, right? I can either, if I receive an attack and I have to forward it more than once, then this number right here is k, right? Or sorry, it'll be a sum of some sum of I, right? Some sort of sum of I. And if we expand this out, it actually ends up being at step I, the number of messages at step I is equal to 1 plus I into I minus 1 divided by 2. And I invite you to look at the paper for the details of how this works out. So that's per step. When you add them all together, you end up with something that ends up being a linear format. So for this specific election algorithm, it ends up actually being at most, so for the sum of over all I of fi, it would be equal at most, so this will be less than or equal to 7n minus log n square minus 3 log n minus 7. Okay, and you can look at the paper for the details, but just to note where the log n's came from, remember that I is the dimension, the number of steps is essentially the dimension of the hypercube. So I is dimension of hypercube, right? And we know that the dimension of the hypercube is equal to log n. That's by definition of the hypercube itself. Okay, it's by definition of the hypercube itself, and so that's why you end up with these log n's. They pop up from these things, but they square and they end up being less than n. So in the end, all of this stuff becomes O of n. Okay, and you also have a broadcast. So once you find the leader, the leader broadcasts it out, which is just another O of n. So in total, it is an O of n algorithm. And that is all. Thank you.